Hi guys, today I'll be talking about the DAC algorithm, what is also known as divide and conquer algorithm. So in my previous videos, I have talked about like the recursion, reconciliation, and reconciliation solving. These are the three things which forms the basis of like the DAC algorithm. So why do we need a DAC algorithm? So we have finished this recursion. When a function calls itself, it is known as recursion. And what is reconciliation? Reconciliation is a relation in which you write a function in terms of its smaller input, and we can solve the reconciliation using three methods, which you have like the substitution method, the recursive tree method, and the master theorem. So let's get to the DAC part. So what is DAC? The full form of DAC is divide and conquer algorithm. It is an algorithm like to solve problems. Let's say you have a very big problem and you don't know how to solve that problem. What DAC algorithm says that if you have a big problem, you divide the problem into small chunks, solve this small chunks. Just a minute. Divide this problem into small chunks, solve these small chunks using recursion, and then combine them to get your solution. So what are the steps? Like if you have a big problem, what you will do is like divide the problem into smaller chunks, solve the subproblems or smaller chunks using recursion. Next, what you will do, you'll combine them. Combine the subproblem solutions to get the final solution. So that is what I have written here. You have a big problem right here. You divide it into smaller chunks. You solve the smaller chunks using recursion, and the results of this you just combine together, and you get the final solution of this big problem. So if I write it in a good way, let's say you have this big problem. What you do, you divide it. Let's say you divide it in three parts. Subproblem 1, subproblem 2, subproblem 3. And this is the problem. And what you do, you like, this is known as divide section. It's the dividing thing. Dividing, like, yeah, you are dividing the bigger problem. You solve this using recursion. You get solution 1, solution 2, and solution 3. This part is also known as conquer. Next, what you do is like, you combine all the solutions to get S. So S1 plus S2 plus S3. This is known as combine. So you are dividing, conquering, and combining. So this is known as divide and conquer algorithm. So now let's go for the pseudocode of divide and conquer algorithm. So let's say I have a divide and conquer function which takes a value a, I, and j. So what is a? A is an array. What is I? I is the first index, which is 0, and j is the last index. So what is your, like, let's say let me take a like example. What you want to do? You want to sort this array A, whose index start from 0 to j. Like 0 is the first index and j is the largest index. J can be anything. So the starting index is I and the j is the ending index. So let's say your array will look like this: 0, 1, 2, 3, 50, 60, 10, 11. So you want to sort this, and your 0, I, this is j, and this is the array A. So what you want to do? You want to like sort it. So according to the divide and conquer algorithm, I will write just the template one. So if small aij, this is a function, return solution aij. So what I have written here, this is the base case. We know in any like any recursive program, we should write the base case, or else the stack overflow will happen. So and now we also know that in recursive program, we should at least know something. Like we should at least know the output of the smallest problem. Like if, because this is where we will return, like this will be the base case. So in recursive program, we should at least know something, like some value of n, some value of a or j, what will be the output? We should at least know that. So this is the base case. Let's say the function, if this is not small, then we'll go to the else part. What in the else part is the main thing in this divide and conquer algorithm, because here we will be dividing and conquering. So let's say divide is equals to let's say a is equals to divide a, I, and j. This divide and this solution and this small, all are functions. So let me highlight this thing. These all are functions, and what we will have code inside them. This divide is also a function. So what like what this divide function will return? It will return a position. So let's say I, j. So I want the middle of this. So what I will do? I will divide I plus j divided by 2. So 0 plus 3, you can 0 or 1, you can take 0 plus 3, 1.5. I will take 2. So 2. The output will be 2 for this. I'm just taking an example. The divide algorithm can be like anything of your choice. You can write anything inside this function. So you can have your own divide logic. So S1, here I will be calling the DAC function recursively, which will be I2. Sorry, I will take this x. Yeah, so x. So what I have done is I have divided the problem into smaller parts, like from I to x. I to x, I am calling this function again, and for S2, I will again call the function a x plus 1 comma j. So I have divided this bigger problem into two smaller subproblems. So and now I will combine s. So s1 s2. This is also a function, and this will be combining our results, and we will returning from here, returning the s. So this is the function combine, and it is like it depends on what algorithm you write inside this combine function. So it will be dependent upon you, like how you want your combine function, how you want to implement your combine function. Here we can see there are two recursive calls, DAC and DAC. And what I have done here, I have divided the problem into two smaller subproblems, and I have used recursion to solve that. So you can see here it is DAC and here it is DAC. So there are four functions I have used, like this small, this solution, this divide, and this combine. These are the functions. So let's see, this part is the divide. Let me take another pen. Yeah, so this part is divide. This part is conquer. And this part is combine. So this is the normal template of a divide and conquer algorithm. So now this is just a template, and so your version, like how you want to define if it is small or not, it depends on you. How will you divide, it depends upon you. How will you combine, depends upon you. This depends upon the specific problems, but this is the template. So how how a divide and conquer algorithm works. So these four functions implementation will differ from problem to problem, because it depends upon the problem, like how you want to divide, how you want to combine, and how you want the solution, and how you define what small is. So these four functions are like will be different from problem to problem. Now next topic is like how we will find the time complexity of the DAC algo. So here I have the DAC algorithm. So let's say I have I have this DAC algorithm here. So I have an array of size n and I to j. So let's say I to j is n elements. So the divide and conquer algorithm for n elements will take, let's say I will write t of n. So here that is what I have written. T is the amount of time required to sort an array of n elements using DAC algo. So this is the total time taken by the DAC algorithm for n elements, sort an array of n elements. Next I have the base case, which is the small. This one will be O of 1, because it will take constant time, because it is a small problem. The so small problem will take constant time. That will be O of 1. So now let's come to the else part. This is where we have the divide and conquer algorithm. So now let's come to the else part. This is the main part where we will do the divide and conquer. So first we are dividing, then we are calling the DAC algorithm recursively. So let's say I to P is n by 2 elements and P to J n by 2 elements. So what you have seen for time complexity for n elements for the DAC algorithm is Tn. So what will be the time complexity for DAC algorithm for n by 2 elements? It will be Tn by 2, because here you can see that I have n elements. So the time complexity of DAC algorithm for n elements is Tn, and like if here I have n by 2 elements, so the time complexity of the DAC algorithm for n by 2 elements will be Tn by 2. And here also I have P from P to J I have n by 2 elements. So here the time complexity for n by 2 elements, for the DAC algorithm for n by 2 elements will be Tn by 2. Now comes the main part. What will be the time complexity of this divide and this combine? So as we have seen, this divide and combine are two different functions. So so the time complexity will be like dependent on the code which is there. If there is a like a loop in there, so the time complexity will be n. If there is a like no loop, then time complexity will be O of 1. So I will take this as f of n, and also sorry, this one will take as f1, fa of n, and this one I will take as fb of n. This will depend on the algorithm, what like the code you will write in these two functions. So here I will write fa of n plus t of n by 2 plus t of n by 2 plus fb of n when n is larger. So this is the like the time complexity. So what is f of n? Time required for dividing. What is fb of n? Time required for combining. And what is this? This is the time complexity of like time complexity for the DAC algorithm for n by 2 elements, and this is for n by 2 elements. So this is the like DAC algorithm, and this is the conquer time. Now if we simplify the equation, we will get t of n is equals to, I will combine these two as f of n and this 2 as 2 n by 2 t n by 2. This will be f of n. So this is the like divide and conquer time, and this is this is the divide and combine time, and this is the time, and this is the time taken to conquer, and this is the whole time. So these equations can be written like this: t of n, a of t n by b plus f of n, where a is the number of subproblems, n by b is the size of the subproblem, and f of n is the divide time and combine time. So divide and conquer relation, like divide and conquer recurrence relation, can be written in this form. So all divide and conquer recurrence relation will look like this, and this recurrence relation can be solved using Master's theorem. So this is how you can find the time complexity of any divide and conquer algorithm. Here we get a t of n by b plus f of n. So most of the reconciliation for DAC algorithm will look like this. Yeah, so thanks for watching the video. Please like it if you liked it. So as we have seen, like to find out the time complexity of DAC algorithm, we have used this recurrence relation of the DAC algorithm to find out the time complexity. So here's interesting, like you can see that the DAC algorithm is a recursive program. So we can say that we can use the same recurrence relation, like the same recurrence relation to find the time complexity of a recursive program. So both are like same. The way we find out the time complexity of the DAC algorithm will be same as finding the time complexity of a recursive program. So it will be same. I guess in the previous video we have seen like how we have found out the time complexity of DAC algorithm. So it was like DAC A, I, and J with small return solution, else divide Aij. Solution 1 will get DAC AI E. Solution 2 DAC AI A E plus 1 J. This is equals to combine, and we will return S. So this was our DAC algorithm, and this was like a template. You can have your own divide logic, you can have your own combine logic. So we have found that the time complexity of this is T of n. So T of n is the time complexity of DAC algorithm. So for this is the T of n. This is small. This is a small problem, and we know this is the base case. So base case we have O of 1. Because it's a small problem will take small time, so it will be O of 1. So we'll get T of n is equals to O of 1 when n is small, and when n is large we will go to the else part. So what is in the else part? else part we have the divide and conquer algorithm. First we are dividing, then we are calling DAC recursively. Let's say I to j is n elements and we are dividing it. So n by I to p is n by 2 and p plus 1 to j is equals to n by 2. So for DAC time complexity for n elements for DAC algorithm was t of n. So time complexity for DAC algorithm with n by 2 inputs will be t of n by 2, and the same thing will be here, t of n by 2. What we got is this 2. And what will be the divide algorithm? It will be fa of n. We don't know what is inside this algorithm because it's a function. Inside this function we can have any code. So according to that code we will find the time complexity. If that code has loop, we will take this as n. If it doesn't contain any loop, we will take it as like constant time. And what is the combined logic? We will take it as fb of n. So fb of n is the time complexity for combining. So the actual fb of n will depend on the what code is inside this combine function. The same thing as what it was with divide. So if we have a loop, we will have one n. If we don't have any loop, it will be like a constant time. So total we get f a of n plus t of n by 2 plus t of n by 2 plus fb of n when n is larger. So what is f of n? This is the divide time, this is the conquer time, and this is the combine time. So we will like combine these two. So we will get t of n is equals to O of 1 when n is small, and t of, we have 2 t n by 2, so 2 t n by 2, so we will combine them, 2 t n by 2 plus f of n when n is larger. So this is the time complexity of DAC algorithm, and you can see that the DAC algorithm is also a recursive algorithm, because here I have recursive call, here I have recursive call. So to find out the time complexity of recursive program, we can follow the same approach we have followed in DAC, because DAC is also a recursive program, so the method will be same. But here comes the next question, like previously what we have done. So next we will see how to find the time complexity of a recursive program. So the basic step, the first step of finding the time complexity of a recursive program is to write the recurrence relation for time. To write the recurrence relation of that recursive program for time. But previously we have written recurrence relation which was not for time, which was for value. So what do I mean by that? We are writing the recurrence as it is, like here it is n is equals to 0 or n is equals to 1, we will return n, or else n into factorial of n. So previously what we have written, like fact of n is equals to 1 or 0 if n is equals to 1, I mean n is greater than 0, greater than or equals to 0, sorry, less than or equals to 1, else we will do n into factorial of n minus 1. So here you can see we have writing the recurrence as it is in the code. So this we have written this recurrence relation. So solving the recurrence relation will give us the value of fact of n. So while we are writing the recurrence relation as it is here, so if we write as it is, it will be for value. So if we write as it is, and the solving of this recurrence relation will be for the value, which is the fact of n. So how do we know it is for value? Like if we write as it is, then it is for value. So what is this fact of n? Like this fact of n is the value of fact of n. So I want to tell you one thing, like if we write a recurrence relation, we can write recurrence relation for various things. Like here we have written for value. Now we can write recurrence relation for time, which is t of n. So what is t of n? T of n is the time taken by this fact of n. Like what is so what is this t of n? T of n is the time complexity of f of n. I will write it, t of n is the time complexity of f of fact of n. So now I will be writing this recurrence relation for time. So whenever you are writing a recurrence relation for time, you should think about loops, because time complexity is all about loops. So when you are writing a recurrence relation for finding out the time complexity, you should always think about loops. So you should find where are the loops in the program. So now let's see this part of this program. If n is equals to 1, so we can see that there is no loop here. So the time complexity will be order of 1 when n is equals to 1. Now I will come to the else part. Here we can see we have this fact of n minus 1 and n into fact of n minus 1. So we have seen the fact of n, the time complexity for fact of n is t of n. So what is the time complexity of fact of n minus 1? T of n minus 1. So we will write t of n minus 1. And there is no loop here, we can see. So if there is no loop, we don't have to write anything. Like if there is no loop, we don't have to write anything here. So we can see there is no loop here. So we can write, if there is no loop, we will write constant. If there was a loop, we would have written like n. If there was a loop inside a loop, we will have written n square. So if there is no loop, we will write c. So when n is greater than 1. This is the time complexity. How we write? This is the recurrence relation for time complexity. This was the recurrence relation for finding the value. This is the difference. You can write recurrence relation for many things, but if you want to find time complexity, you have to write the reconciliation for time. If you want to find the value, then you have to write the reconciliation for value. So now if you solve this reconciliation, what we'll get? We'll get the time complexity because we have written the reconciliation for time. So let's solve this reconciliation. So we will be using substitution method. So n minus 1 will be t of n minus 1 plus c will be t of n minus 2 plus c. So if we put this in this, we will get t of n is equals to t of n minus 2 plus c. Now again, if I compute this t of n minus 2, I will get t of n minus 2 minus 1 plus c. So it will be t of n minus 3 plus c. So if I substitute these values in this, so we will get t of n is equals to t of n minus 3 plus c, and this to c. 3c. So now if we do this k times, what we will get? T of n is equals to t of n minus k plus kc. Because when we did it for 3 times, we got 3c, so we got kc. Now I want to make this 1, so n minus k should be 1. So what I get? N is equals to, k is equals to n minus 1. So we will put the value of k here. So we'll get n minus 1 plus n minus 1 c. So what comes at t of 1 plus n minus 1 to c. So we got here O of 1. This I got from this. So plus n minus 1 into c. So the time complexity will be b of n. Because n minus 1 to c, this is constant. So I will get b of n. This will be the time complexity for factorial. So how did I get this? I got this by solving this reconciliation which I wrote for time. Now if I solve this reconciliation with substitution, I will get different answer because this reconciliation I have written for the value. So I will also solve this reconciliation using substitution method, and I will show you that both are different. So if I write this reconciliation again here, fact of n will be equal to 1, I guess. Yeah, I have written it a bit like it will be 1. I have written it wrong. 1 for n is less than equals to 1, and it will be n into fact of n minus 1 when n is greater than 1. So let's solve this. So fact of n I can write in as like f of n is 1, n is less than 1, n into f of n minus 1 when n is greater than 1. So f of n is equals to n, f of n is equals to n into f of n minus 1. So let's do the substitution method. F of n minus 1 is equals to n minus 1 into f of n minus 1 minus 1. So I will substitute the value of this here. So what I will get? F of n is equals to f of n minus 2 into into n minus 1 into n. Right? Yeah. So now I will solve this. So f of n minus 2 will be equals to f of n minus 3 into n minus 3. So if I substitute the value here, I will get f of n is equals to f of n minus 3 into n minus, just a minute, I got n minus 2 into n minus 1 into n. So if I do this like k times, we will get f of n minus k into n minus k minus 1 into n of into n minus k minus 2. This will go on till n. So I want this f of n minus k is equals to this to f of 1. So f of 1, I know the value of f1 because 1. This will be the base case. So n minus k is equals to 1. So n will be, k will be n minus 1. So if I put the value of k here, I will get f of n minus 1 into n minus 1 minus 1 into n minus 1 minus 2 dot n. Till n I have to go. So this becomes f of 1. This becomes 2. This becomes 3. And I will go up till n. So this is 1, this is 2, this is 3, up till n. So this becomes n factorial. So solving this reconciliation, I am by substitution method, I am getting n factorial, which is different from this one. So I am getting different because I have written this reconciliation for value and I have written this reconciliation for time. This is the difference, which is very important to understand. Thanks for watching the video.